Okay, merci. Okay, so welcome for this last lecture. So for this last lecture, we will talk a little bit about Ricci flow. The goal is to give you, if you're not familiar with the notion, is to give you a quick start so that you can follow Professor Bamler's lecture next week. So this is a big topic, like all those, and quite technical in some parts. So maybe there will be less detailed proof than there used to be in the other lectures, which proofs were not so detailed, but they will be maybe even more sketchy than they were in the previous lectures. Okay, so first let's give a definition of what the Ricci flow is. So the Ricci flow, I think, yeah, I'm gonna restart my screen share because here it's not updating. Okay, maybe I'll do it like that. I'll blame the heat, maybe. Okay, let's get back, sorry. Okay, I think we're good. So what's the Ricci flow? The Ricci flow is an evolution equation for one parameter family of metrics. So you take a family of Riemannian metrics on a fixed manifold. So, whoops, let's remove notifications maybe. Sorry about that. Here too. Okay. So it's a one parameter family of metrics, let's say smooth, such that the derivative of g with respect to this time parameter is -2 times the Ricci curvature of g at times t. So these are symmetric two tensors on each side, so at least the equation makes sense. The 2 is just a normalization factor. The minus is very important actually because so if you try to, for instance, in a simple system of coordinate like harmonic coordinates, for instance, or normal coordinates, the Ricci curvature in terms of the coefficient of the metric kind of looks like minus a Laplacian in some sense. So you have to be careful. It's actually degenerate, but we'll not go too deep into that. But so if you just look at the coefficient, this more or less looks like del u over del t equal Laplacian u. And if you don't put the minus, you would have a reverse heat equation, which is usually not a good idea. So the minus sign is very important. Okay. So this is a kind of a geometric, because it's expressed in purely geometric terms, heat equation for Riemannian metric. Just as the mean curvature flow, which Felix introduced and gave lectures about, is a heat equation for submanifolds and a geometric heat equation for submanifolds in an ambient manifold. Okay. So what do we do with that? So maybe let's first state a theorem, which we won't have time to say much about the proof. So if let's say mg naught is a compact Riemannian manifold. Then there exists g of t, a family of metric, for t in some half-open interval, such that basically what we're saying is that the Cauchy problem has a unique solution. So first, at the initial time, we have g naught, and well, the equation is true. Okay, and moreover, maybe it's just we have a long time existence criterion, so which can be stated in this way. So if you don't have long time existence, then the curvature must blow up. So R of t would be well, I should take a supremum in space, because so we have a space and time variable here. Need to be a little careful. So there must be points if the solution is undefined for all future times, there must be points where the curvature is blow up. Actually, yeah. Okay. Okay, so now let's give some examples first. Well, the really easy ones, the really easy one is to assume that G naught is Ricci flat, so Einstein with vanishing Ricci curvature. Then we have a maximal solution, and it can actually be extended on all of R. So this is a solution. You can do a little better with by assuming that G naught is Einstein. So yeah, Ricci flat matrix corresponds to some kind of fixed points of the Ricci flow. Okay. Now assume G naught is Einstein. So Ricci of G naught is equal to K G naught, let's say. Then let's make an ansatz and look for a solution G of t, which will be of the kind phi of t times G naught. So just homothetic of the initial metric. Then the Ricci tensor as a 2-0 tensor, this is important, of G of t is just the Ricci tensor of G naught. So as a 2-0 tensor, the Ricci curvature is not sensitive to scaling. Okay, so this is good. So Ricci minus is equal to that, and on the other end, if I compute the derivative of this one parameter family of metric, it's phi prime of t times G naught, and G is a Ricci flow here, if and only if. So phi prime is equal to minus 2k, if I'm not mistaken. And so that tells us that if we want to have G naught as the initial condition, so G of t will be equal to 1 minus 2 kt times G naught. So we are having some problem here, because when k is not enough, this coefficient can vanish, so we have some kind of collapsing, so which will depend on the sign of k. So let's make pictures now. So assume k is positive. So if k is positive, what you have is a sphere. And so this factor will be strictly decreasing. So we will be shrinking linearly our sphere from t equals 0 to here, t equal 1 over 2k. So if k equals 0, we already knew what was happening. So maybe let's let's think of a torus with a flat metric. Then it doesn't move by the Ricci flow. And if k is negative, so let's think, for instance, of an hyperbolic surface with constant curvature -1. Yep, sorry. And then it's homothetically expanding. Okay. And so t equals 0 does something. And it can be extended in the past up till down minus 1 over 2k, since k is negative. So we see here some special kind of solutions. So they only move by homothety, and they are defined on unbounded interval. A bit of vocabulary. So solutions which exist for all times in the past are called ancient. Solutions which exist for all time in the future, like in this third case, are called immortal. And solutions which exist for all time on both directions are called eternal. And you see that the existence of such solutions in the manifold seems to be sensitive to the sign of curvature. And we will, though there are some, it's not that clear. Okay, maybe let's give some other examples. So you can take products of solutions R solution, and one big example is the shrinking cylinder. So here the spherical factor will shrink while the flat factor will stay the same. So this will be something like that. And at the singular time, so which would be here, I guess, 1 over 2 n minus 2, because we have the Einstein constant of the n minus 1 sphere. We have collapsing to a line. This will be a very important picture to have in mind, because it's the one kind of singularity that happens in when you try to understand Ricci flow with surgery. Okay, and maybe some other kind of solution, because so those are very simple solutions, but there's another kind of solutions which is little bit more interesting, which are solitons, which in some sense don't move, because we make the following on that. So it's that our metric here, g of t, is of the form c of t, scaling factor, and pulled back by a family of diffeomorphism, one parameter family of diffeomorphism of some metric. basically the metric seems to move, but actually it's just moving by scaling and a change of coordinates. But up to scaling, the geometry doesn't change. Just if you're looking in a fixed coordinate chart, you're looking in the wrong coordinate chart. Yeah. So these solitons were first used in PDEs because when they were looking like for translation invariant solutions of propagations of things and stuff like that. Here the translation invariance is replaced by like a coordinate change invariance. So if you take the time derivative of that at t equals 0, what you get is the following. So on the left you get twice, so if this is a Ricci flow, and here you get c prime of 0, so you differentiate the product and put t equals 0, plus Lie derivative along some vector fields, which is tangent to this family of diffeomorphism at x equals 0. And actually, it's an exercise to show that you can go back here. If you have a metric G0 which satisfies this for some vector field, then you can go back. Usually this guy is called minus lambda. And so this is the equation for a Ricci soliton. And we will say that its gradient, if x is the gradient of some function u for some u from M to R. And if x is a gradient, then you can rewrite this equation because the Lie derivative of the metric in the direction of the gradient is just twice the Hn. So what you get is that, should I put them? Yeah. I'm not sure about my sign choices, if they are really coherent with my notes, but up to changing some convention, it's not a big deal. Yeah, that's okay. Plus Hn of u equal to lambda over 2 g naught. So this is the equation for Ricci soliton, and this allows us to build more examples of solution. For instance, you can look on surfaces, maybe an exercise if you want to get a feel about computation with the Ricci flow. So assume that G is of the form dr squared plus f of r squared d theta squared. So you write that in polar coordinates. And u is a function of r only. So show that, so on the surface, let's say, is a Ricci soliton, a gradient Ricci soliton. If so this boils down to a system of ODE. Maybe with yeah, maybe lambda should be lambda over 2 or something like that. Not on surfaces it's pretty easy. F prime. Oh yeah, that's the curvature here. So that's f second over f. And with that, you can show that there exists soliton with lambda equals 0 on R2. So basically you have several of them. You can take the flat metric is a soliton, but you have another one with positive curvature and which is asymptotically cylindrical. So this is called the cigar soliton. And you get that by, it looks like that more or less. And the thing is that the Ricci flow will move things outwards, but won't. But actually, this will be this will still be a solution. To prove that, you show that u prime and f are proportional if lambda is equal to 0, and that will give you the solution. And you can get other examples, but this is the only smooth one, apart from constant curvature guys, that you get in this setting. Okay, so now we have a PDE for the metric. It's now interesting to look at the evolution of geometric quantities. And when you're new to the subject, it is not easy to take a grasp at what's going on. Basically, the problem is that everything is moving with time, so time derivative doesn't commute with anything. So you have to be careful. Like if you want to differentiate the gradient of a function, the metric depends on time, so the gradient of a function, even if the function doesn't depend on time, will depend on the time too. And it's even worse for the curvature because you have those double covariant derivatives, and those covariant derivatives depend on time. So when you exchange covariant derivative, you have extra terms which comes from the time derivative of the connection, and so on. So it's not complicated, but it's tedious to write down the proof. Actually, the equations are not that bad in the end. We will prove just one, because it's a good, nice way to. It will come back afterwards. So let's look at the evolution of the volume form. And then we will be able to look at the evolution of the volume. So, and for this, we will consider EI an orthonormal frame, choices of orthonormal frame somewhere, at some point. And actually, we will prescribe the evolution of EI in the following way, and you will see why we are doing that. This is reminiscent of what I was saying about Ricci soliton. Sometimes things look messy and don't evolve in a simple way, but maybe it's just because you have not looked at the right coordinate system. Here it's a similar idea. So and assume that EI of t, its time derivative is given by just Ricci, seen as an endomorphism of EI. So, exercise. So that's Ricci with respect to g of t, and as a with an index raised. So maybe Ricci sharp if you want. Exercise. So this evolution equation for the frame preserves orthonormal frame. if you start with one orthonormal frame at time 0, it has no reason to stay orthonormal afterwards. Okay, so now what do we do? So let omega g of t be the volume form of m g of t. Then what do we have? We know that omega g of t of E1 up to En, so the volume form evaluated on an orthonormal basis, is equal to 1. So yeah, let's assume that it's oriented. And then what we can do, also let's differentiate that. Then what's going on? So we have omega dot, let me lose the g of t for 1, of E1 till En, plus omega of E1 dot till En, plus omega of E1 till En dot is equal to 0. But then, so we know who are those EI dot, so plus omega, so here this will be Ricci of EI as a vector of E1. And then, let's not forget dot, omega of E1, Ricci of En. And it's not complicated to see that like you can put like you can either choose a diagonalizing basis for the Ricci tensor at the initial time if you want, or you can just decompose Ricci of E1 on the EI frame, and this will give you that omega dot of E1 En will be equal to the scalar curvature, so the trace of the Ricci tensor of g of t with a minus sign, times omega of E1 En. Okay, there are other ways to do this computation. You could write everything in coordinates if you want. You would have to differentiate the determinant, but that's not too complicated. Yeah, I find it clearer in this way. Okay, so now that we have the volume form is itself satisfies that d over dt of omega gt is equal to minus the scalar curvature times omega g of t. So now we can look at the evolution of the volume. And the evolution of the volume of a solution of the Ricci flow. So this will be equal to the integral of omega. So once again, yeah, if you differentiate integrals, the volume form will be changing. So you have to be careful at first. So, and this is minus the integral of the scalar curvature. So corollary, for surfaces, you get a very nice expression. I won't go too much into the details of the Ricci flow on surfaces. It's a very special business, but with which is pretty interesting. But yeah, I can't resist here showing you what's going on. So if you look at a surface, compact surface, then you have minus the integral of the scalar curvature. In 2D, the scalar curvature is twice the Gauss curvature. So you can use this key of m squared, so the Euler characteristic. And actually, so you actually get an explicit expression for the volume. So which will be volume of m0 minus 4 pi t key squared of m2. And actually, this is the picture we already draw. So, but now we can have something more bubbly, maybe. So something of genus 0. Then you know that the Ricci flow will stop at some definite time because the volume goes to 0, so it has to stop before. And actually, yeah. And actually, what will happen in that case is that it will shrink to a point, but it will get rounder and rounder. We will see when we talk more about the Ricci flow in dimension 3, what's going on. And yeah, and you have similar behavior on when the genus is 0 or negative. You will have up to some scaling for negative for positive genus, negative Euler characteristic, convergence to the constant curvature metric. So yeah, maybe just notice that RF on surfaces reproves the uniformization theorem. So it stays in the conformal class because of the structure of the Ricci curvature in dimension 2, which is very special. And it converges inside the conformal class up to some scaling to the metric of constant curvature. Okay, so we have say something about the evolution of the curvature. We can look now at of the volume. We can look now at the evolution of the curvature. And here I won't make the computation. It's done in the textbooks. It's usually I don't know. Wow. Yeah. Let me look. So I think in the first lecture I talked about Chow and Knopf book. There are also this Chow, Lu, and Ni. And you can look at the computation here of evolution of geometric quantities. Yeah, I don't remember if they do that in full details. 108. Yeah. I guess the proof is not included here, but well, maybe in another chapter. Maybe they postponed it. Okay, anyway, that's so. But one important thing to do, and this is why I introduced here this trick of trying to move an orthonormal basis in an intelligent way, so to keep it orthonormal, it gives you a gauge change. So in a moving frame, like the one I described before, and if you're interested like in eigenvalues and stuff like that, it's not a big deal that the frame is moving. Like that won't change. So the curvature tensor as before, seen as a 2-2 tensor, or as an operator from bivectors to bivectors, evolves by, so it satisfies a parabolic equation, a system of parabolic equation, which is Laplacian R. The Laplacian depends once again on the time, plus something which is called Q of R, which is some universal quadratic vector field on S2 of lambda 2 of Rn. Something which takes a symmetric matrix defined on two forms and gives you another one in a quadratic fashion. We will see what it is in dimension 3. It's not too complicated in dimension 3. In higher dimension, you have to be a little more careful. Okay. And so now, so you can give the evolution of the Ricci curvature, though we won't need it here. And you can also give the evolution of the scalar curvature, which we will use. If you take the scalar curvature, you can take the trace here. Okay, and that gives you the following. And so all these geometric quantities tend to satisfy some kind of what are called reaction diffusion PDEs, or system of PDEs. So the diffusion is the Laplacian term. And the reaction term is this nonlinear term that you have. Oh, yeah, I forgot the norm. Is that what you were saying, Laurent? Okay. Yeah, I was too quick. And so this is the reaction terms. And how do you use that kind of equations? Okay, so how to use those evolution equations? Well, the thing is the following. So how do we? Yeah. So one key tool here. It's not the only one. You can do integral estimates if you need to. There's a lot of things which can be done. But one of the key feature in Ricci flow is the use of maximum principle. And maybe let's do a simple application of that, which might come up in some talks or lectures afterwards, and which has nothing to do with Ricci flow at first sight. So let's prove the following proposition. Let Mn be a manifold. Should I put the metric in the data? Yes, I guess. Riemannian manifold such that, so G naught is scalar flat, and Mn compact manifold. Otherwise, you would have counter examples. Mn has no metric G with positive scalar curvature. Let me give a conclusion to that story. Then M is actually Ricci flat. And we will see how we can use the evolution equation for the scalar curvature here. Okay. Okay, so how can we prove that? So I guess this is due to Kazhdan, which I'm probably butchering the spelling. Sorry. So how do we prove that? So this is not the original proof of Kazhdan. This is a later proof because Kazhdan proved that before Hamilton introduced Ricci flow in the early 80s. So how do you prove that? So consider the Ricci flow G of t defined on some time interval such that which start at G naught. Then we know two things. So if we look at the evolution equation for the scalar curvature, so we said that it was the Laplacian. So I will more and more drop time dependence. Whoops. In those equations. In particular, it's bigger than just the Laplacian of S. And S of G naught is equal to 0. Yeah, actually, I'm not sure why I... Yeah, maybe I should know. The result is more striking like that. So start with a metric with non-negative scalar curvature on a manifold which has no metric with positive scalar curvature. Then it is Ricci flat. Okay, so we have this evolution equation. So this function is a super solution of the heat equation. And they do satisfy a maximum principle. Hence, we have an alternative of the heat equation. So with non-negative, let's say, initial condition. And the proofs are the same as in RN, more or less. You can look at the book of Chow and Knopp for a proof with a non-negative initial condition. Thus, we have an alternative. Either S G of t is identically equal to 0 for t positive, wherever it makes sense, or S G of t is strictly greater than 0. So this is the strong maximum principle. The weak maximum principle will tell you that starting with something non-negative will give you a non-negative solution afterwards. And the strong one will tell you that it will become immediately strictly positive, or otherwise it will stay at 0. But this is not possible, since we have assumed that M has no metric with positive scalar curvature. And as g of t is equal to 0, and now if I plug that, so this is true. But then, so if the scalar curvature is identically 0, so I can get here. Yeah. So now I plug the fact that the scalar curvature is identically 0 inside the evolution equation for the scalar curvature. So let me maybe put yeah. So the time derivative of the scalar curvature is equal to the Laplacian of the scalar curvature plus twice the norm of the Ricci curvature squared, and the Ricci curvature of g of t is equal to 0, and then you let t go to 0. Nobody's moving once Ricci is equal to 0. Okay, so that gave a proof of a geometric result using Ricci flow and the maximum principle. Okay, so maybe a corollary of the same method, the proof rather than the, is that lower bounds on SG0 are preserved by the Ricci flow. So if you start with a manifold which has, let's say, a scalar curvature bigger than some constant, then it will stay true as long as the solution exists. But we can actually do better. Okay, let's refine a little bit. So here we have compared to the heat equation, but we can actually compare to, and this gave us comparison to constants, more or less. But we can actually extract more information. Okay, so still start with so we have this Ricci squared term, which gives us an evolution equation for the scalar curvature, which is not a closed equation. Like we need extra information from the Ricci curvature to compute the evolution of the scalar curvature. But we can get an inequation which is closed in some sense by looking at the following. So the scalar curvature in terms of matrices is just the inner product of the Ricci curvature and the matrix. So you can apply Cauchy-Schwarz inequality. So this norm of g squared, and this is a trace. So this will be n, hence what that tells us is that now I can use that to show this not equal, sorry. That would be equality if we have something where if Ricci is diagonal, is a multiple of the matrix. So we have equality for Einstein manifolds, but we still get that. And so there is a maximum principle here, which is a comparison. So which tells you that basically so inside, when you have an equation or an inequation of this form, if you understand what's going on when there is no diffusion, then you can say stuff about the PDE. So it's an ODE PDE comparison principle. So let me state it maybe. So theorem. So I guess in that form, maybe you found it for the first time in Hamilton, but people doing parabolic PDEs have used that for ages. But like they were usually not working on manifolds or stuff like that. So assume that, yeah, maybe let's just write it for this equation. We will use it for that. Assume that S at time 0 is greater than some constant sigma. And let U be the solution of the ODE you would get if you'd get rid of the Laplacian. So U prime equal 2 over n times U squared, and which starts at that lower bound. Then, as long as it makes sense, S, you have a uniform in space lower bound here. And actually, you can solve the ODE as just like a college student and a freshman. And so this would be, so I use sigma. So this is sigma over 1 minus 2 over n sigma t. Okay? And so this is good. In particular, so corollary again. So, and this is in the spirit of what we were saying, that when you have positive curvature, then you tend to have a finite time of existence. So if I have a solution, so let's say defined on 0 big T, with scalar curvature at the initial time greater than sigma, then the existence time can be bounded above by whenever this lower bound for the scalar curvature blows up, which is n over, no, yes, okay. So if sigma is small, if sigma is big, the existence time is very small. Yeah. And there are actually interesting results, like under some assumption. So this bound is attained for round spheres, for instance, or any Einstein manifold. And you can try to see whether it's optimal or not. And there are some cases for the sphere. So if you have something which has a positive curvature, and so you need to make to break scale invariance at some point, but in some sense, if you have positive curvature and your time of existence is as big as it can be, then you're very close to being the sphere. Okay, so so far we have only used our evolution equation for the scalar curvature, and in the last half an hour now, I will try to show an example of how you can get advantage of this system here. So we had a maximum principle for a single equation here. So what we will need will be a maximum principle for systems. So let me state that. For systems. Okay, so we will just state it for the evolution of the curvature operator here. So Mn g of t be a solution to the Ricci flow. We can assume that M is compact to be safe. If it has bounded curvature, it works also, but it's still unclear in some cases if you can really make it work, I think. In very non-compact complete case. So now I consider some K included in that set. So what is that? It is the space of curvature operators. By that I mean 4 tensors, or two tensors actually, which have the same symmetries as the curvature operator. So the lambda 2 here is what will give you the fact that you can exchange the first two entries while changing the sign. The fact that it's symmetric is the Rxyzt is equal to Rztxy, and the B stands here for the Bianchi identity. And so this is a tensor on a 4 tensor on Rn, which has the same symmetries as the curvature operator. And I take a set of 4 tensors like that. So, and I look at and I ask for it to verify the following condition. So K is closed and convex. And K is invariant, stable. Maybe I should say stable. People say invariant, but I think stable is a better term here. Is stable under the flow of the vector field, which appeared, which we encountered in the evolution equation for the curvature operator, Q. So that means you have, so in that space of curvature tensor here, you have your set K, which is convex, and you assume that if you start inside and follow Q of R, then you will stay inside. So basically this can be checked by saying that at every point in the boundary of K, then you're pointing inwards of K, okay? And basically, then you can write this Am I forgetting something? Oh yeah, I forgot a condition. So okay, and third condition, K is invariant under the action of the orthogonal group on that guy. So you can make orthonormal change of basis And this set of curvature operators shouldn't change when you do the change of basis. So basically, for instance, like if we didn't have, if we had like S2 of Rn, just symmetric matrices on Rn, which in dimension 3 will be the case actually, that means that your condition can be stated in terms of the eigenvalues of these matrices, because like orbit of the orthogonal group on symmetric matrices are completely described by the eigenvalues of the matrix. Okay. So yeah, I said I was stating a theorem. So now I need to state it. Enough hypothesis. So if for every x in M, the curvature operator of that point at time 0 belongs to K. So what I mean by that is that I can identify, you choosing an orthonormal basis of the tangent basis, this S2B of lambda 2 of Rn with a fiber of the vector bundle of curvature operators. Okay. And so I can put K inside that. I will get something well defined since I'm ON invariant. And then the curvature operator of my manifold is a point inside that space. So that makes sense. This is okay. And so this is my maximum principle. And so you can do a lot of stuff in with that. Okay. Okay, we will see some applications right after in a couple of minutes, but okay. And a big application of this circle of ideas is the theorem that I wanted to give you an idea of the proof. So I will do like pre-Perelman Ricci flow, and actually the genesis of the origins of Ricci flow. And so I will give you an idea of the proof of the first non-trivial theorem about Ricci flow. So that was proved by Richard Hamilton. I think the paper was published in 1982. And I will state it in I'm a geometer, so I want to prove geometry theorem. And behavior of PDEs is fine, but I'm using it as a tool. So the theorem I really want to prove is the following. So let M3G compact three manifold with positive Ricci curvature. We'll put a 0 here. Then M3 is diffeomorphic to a manifold with constant sectional curvature, which will be a quotient of S3 by a finite subgroup of O4. Oh, sorry. So one, in particular, if M3 is simply connected, then gamma is trivial because it's the fundamental group of M, and M is diffeomorphic to S3. So what Hamilton had in mind at that point was maybe we can use this kind of ideas to give a proof of the 3D Poincaré conjecture, a program which will be fulfilled by Perelman in 1982. Yeah. Thank you. Yeah, so this initiated a long roll, like 20 years of work, which culminated in the, well, maybe not because it's still continuing, but which led to the proof of the Poincaré conjecture by Perelman and Thurston's geometrization conjecture. Okay, so we have a little more than 20 minutes to tell you how it goes. Okay. Okay, so sorry, I don't. Yeah. So the remark on the fundamental group is that if you assume in that theorem that M3 is compact and simply connected with positive Ricci curvature, then the conclusion holds, but you know that that guy on the right will be simply connected. So that tells you that there's no group and M is just diffeomorphic to S3. So that gives you the so it's a step, some kind of a step towards proving that any simply connected compact three manifolds is diffeomorphic to S3, which is the Poincaré conjecture. So you do have that, but under a very strong geometric condition. Okay. Okay, so what did Hamilton prove, and what we won't prove is the following. So, but we will prove something which is just enough to get the geometric conclusion, and which is an idea which is very powerful, which will introduce some tools which are very useful. So let M3 G of t t in 0t be the solution of the Ricci flow with G of 0 equal to naught. Since Ricci is positive and M is compact, Ricci is strictly positive, and the scalar curvature is strictly positive, so T is finite. And Hamilton actually proved. So we know that the curvature is blowing up when T goes to big T. So that was part of the existence theorem, which was actually also proved. This existence and uniqueness theorem. Maybe they didn't have uniqueness. Yes, it did. Oh, yeah, I'm not quite sure. You haven't looked at the paper in a long time. So the curvature blows up, so we cannot have really convergence. Yes, CPT is compact. But we can rescale stuff, and the good rescaling is the following one. T goes to big T, not infinity, where G infinity has a constant sectional curvature. And that tells you that any manifold which has constant sectional curvature is diffeomorphic to a constant positive sectional curvature is diffeomorphic to a quotient of the sphere. And so once we do that, we're okay. As I told you, the behavior of the PD is not my main interest, although it's very useful to know that. So we will use another argument, even though most of the steps we will use a shortcut which won't give us the convergence, but the main ideas from Hamilton's proof will be here. Okay, so now comes the application of the maximum principle. So okay, so what is R So the curvature operator in dimension 3. So R is going from lambda 2 of Tm, which is dimension, which is dimension 3. Maybe let's write. I didn't write the. So the convention is the following one. So if you want to express this curvature operator in terms of the 4-0 curvature tensor, this is what it is. Okay, in particular, of let's say E1, E2 inner product with E1, E2 is just the sectional curvature of the plane generated by E1 and E2. Now, so E1, E2, E2, E3. So we're in dimension 3, so this is an orthonormal basis of lambda 2 of Tm. And actually, since so this gets much more complicated starting in dimension 4. But in dimension 3, any orthonormal basis is of this form. And for some orthonormal basis of R3, so R is symmetric. So that means that we can diagonalize it. With E1, E2, E3 as eigenvectors. And so R can be written in the following form. So let me try to be consistent here. So at each point you have that. So at each point. And you can assume, for instance, that lambda should be the sup over all planes pi in TPM of the sectional curvature of pi, and nu should be the int. Grassmannian compact. The Grassmannian is compact, so you can take a minimum of that for any two planes here. So here, this curvature operator can be seen as a representation, if you choose a good basis, has a diagonal matrix where the diagonal entries are sectional curvature, some preferred planes. Okay. Okay, so now to understand Ricci flow in that setting, so we need to understand the ODE R prime equal Q of R. And we need to understand that for any initial condition. And since Q is O of n invariant, we can restrict ourselves to diagonal matrices. Then what is Q of R? Yeah, I don't know why I put dependence on t here, it's useless. So it's lambda squared plus mu squared plus lambda nu, and nu squared plus lambda mu. So r prime equal q of r is then equivalent to the following system of three of these. Like that. Okay, so now if we find convex ON invariant condition which are preserved by this ODE, convexity, you have to be a little careful. It's not convexity in lambda mu nu, it's convexity in the matrix. So I won't delve too much into that. But once you have found something we express in terms of these eigenvalues, to check whether it's defined the convex sets in the matrices, basically you use like convexity of the lowest eigenvalues and concavity of the biggest eigenvalue, and this, and trying to write things down, will give you the convexity of the required set. But okay, an application of that, which my undergrad suffered on in my differential equation lectures, that if Mn G0 has non-negative sectional curvature, then the Ricci flow, yeah, maybe let's not put an n here because it's false starting in dimension 4. There are counterexamples. And 3G of t also has non-negative curvature, non-negative sectional curvature. For t positive, yeah, maybe let's write the interval of existence instead. Okay, so how do you prove that? Well, you look at the system here, pick a solution. We start with, so these are the sectional curvature, and there's the smallest one among them. So the proof is just observing that positive sectional curvature, non-negative sectional curvature, is equivalent to lambda greater than 0, mu greater than 0, and nu greater than 0. And this is stable. Maybe let's call this system S. This is stable under the flow of S. Because like you start with that. So assume at some point one of the sectional curvature becomes negative. And look at what's going on when it crosses the boundary. And when it crosses the boundary, one of those sectional curvature is 0, while the other two are greater or equal than 0. And then, so let's assume like nu vanishes while lambda and mu are greater than 0. And then, so this term on the right will be non-negative. You have to play a tiny little bit again with that, but it works. Like if lambda and nu are strictly positive, you're done. If another one is vanishes, then actually you're on the axis, on one of the axes in the lambda mu nu space, and the axes are solutions. So by uniqueness, you cannot be here. Okay. Okay, so I have 10 minutes left. That's not enough. Okay, so I will. So Ricci curvature, it's more or less the same business, but you need to translate that. And it's sum of two sectional curvature, which is positive, so that gives you that. And you can play the same game. So assume that at one point, one of those three quantities along the solution of the vector field vanishes, and compute the derivative at this point. And you will see it needs to have a sign and so on. Okay, so this is preserved too. The same thing goes for, and this is more interesting maybe, for this, so with C less than 1/3. And basically you show that it's more or less equivalent to mu plus nu bigger than something, some C prime times lambda. I think that's it. Yes, some C prime which depend on C times lambda. If you assume that so you can always assume that the eigenvalues are in increasing order. That's not a big deal. So, and what this tells you is that if so, remark that oh no, sorry, this is false. So C times the scalar curvature. Remember that the scalar curvature is the trace of the Ricci tensor. So if C is equal to 1/3, then you have a matrix of trace S whose every eigenvalues is at least S over 3. That means that Ricci is just S over 3 times the identity. So this is called the pinching of the eigenvalues of Ricci. So it gives you a very strong control. But this is still not enough to show that what we have. What we would like, so maybe, let me draw a picture. So we have this space of lambda mu nu. And let me assume that on that axis, I put the scalar curvature. So what I would like to do, so what we show here is that we have some kind of cones, and actually we have a one parameter family of cones which gets closer and closer to the axis, and my vector field q is pointing inwards. So this would be like Ricci greater than C SG times G, which is a convex cone inside this lambda mu nu space, and corresponds to something convex in the matrix too. Okay, but this is still not enough. But what can be shown, it's again due to Hamilton, is that for any G naught with which satisfies the hypothesis of the theorem, and there exists a constant C and some delta, such that, so I will write something here which is a scale invariant measure of how pinched is the Ricci curvature. Sorry. So if this has zero norm, then Ricci is equal to a multiple of the identity. M is Einstein, and we're more or less done. We will make that scale invariant. And what one can show is that this is true. So, and this is once again computations using the maximum principle. This one is a little bit more involved than the previous one, so that's actually okay. Now 5 minutes. Okay. Now we have all the ingredients to prove the theorem, except one, which I will be very brief about. So instead of looking at convergence of the Ricci flow, we will do something that Felix talked about. We'll try to, instead of knowing the precise behavior of the solution as t approaches the singular time, we will look at the tangent solution, like the singularity profile, which we, so we have, maybe let me make a picture. So we have our manifold, which is doing something. And something's going on when we arrive at this singular time t. And what we will do is we'll take that, zoom that in, get something else, which still stops at some singular time t. Maybe not the same, but. And then we will continue and we will iterate that process. We'll zoom more and more and more. So, oh no, yeah, that's s to the power delta. Okay. And so what do we do? So we pick xi, ti, point such that so we pick a point where a sequence of points and time such that the curvature is blowing up. So that sup of x ti. So the supremum is equal to the norm at xi. And so we know that this is going to plus infinity, where ti is some sequence which is going to the singular time. Next, we define a sequence of Ricci flows. It's a good exercise to check that these are actually Ricci flows. So ci g of ti plus t over ci. So this is a parabolic rescaling. And then we would like to extract a converging subsequence. Then what do they satisfy? So they have bounded curvature at 0 actually. At t equals 0, and it's bounded by 1, and with a maximum principal argument, again involving the norm of the Riemann curvature, you can show that you actually have a uniform bound on some like 0 epsilon time interval. Okay, so what else does it have? You can show, and this is quite hard, even though there are probably shortcuts in that situation. So maybe the quickest modern way, or the most efficient modern way, because it's used everywhere, is to use Perelman no local collapsing. So that will tell you that the injectivity radius at xi for the metric gi of 0 at the point xi is bigger than some epsilon prime, let's say. And those two, so now we are back at the first, more or less back at the first lecture where we talked about smooth convergence. This is actually enough to show smooth convergence. So gi of t, a sequence of Ricci flow, converges smoothly, and this is where the Ricci flow helps us a lot, because the what? because the smoothing effect, the parabolic nature of the Ricci flow, gives us smooth convergence, whereas if we're on a fixed manifold, we would only have C1 alpha convergence. But then, so we said that this last estimate that we had was scale invariant. But so what we get is that Ricci of gi of t minus si over 3 gi squared over si squared is less than c over s. Yeah. So this on the left is scale invariant, and then you have to look at what the scalar curvature becomes. And basically it's of the order of ci to the power delta. And so this is going to 0 as I go to infinity. So, and that implies that Ricci of g infinity is equal to s infinity over 3 times g infinity for every t. And from there you see that the limit is Einstein. Moreover, g infinity is not flat because you rescaled it in such a way that the curvature is 1 at that point xi. So since you have convergence of the curvature, since we have smooth convergence, then we get that. So g infinity is not flat, hence, and the Ricci curvature is non-negative. So g infinity has a constant sectional curvature. So that tells you that m infinity, g infinity, so this here, when on this convergence here, like it's a pointed convergence. Yeah, maybe I should be clearer here. So we have to be a little careful. Maybe the topology could have changed, but since the limit is compact, as we explained a little bit, or I gave that as an exercise, I guess. That tells you that each manifold on the for I big enough, the manifold is different, is diffeomorphic to the limit, but we have only one manifold. So see lecture 1. Okay, and this idea of blowing up the solution is a very fruitful one. So I wanted to give you one example, and yeah, maybe let me give a pointer here. Let me say that this is Hamilton's compactness theorem. So thank you all for your attention. Yeah, I'm 5 minutes late. Sorry. I hope I will have helped you to follow the other lecture that are taking place, the other beautiful lecture. I hope you learn something, and thank you for your attention. Any questions? Pardon?
We are collapsing under the heat. On a fondu.
I don't know why, but I don't hear you very loud. Let me. I didn't get it. Yeah, I had a lot to cover today, so I didn't put any poll today.
Okay, in any case, we want to thank you for this lecture, series of lectures. Thomas has been very asking at the very last minute, and we did it quite a busy year. So thanks again, Thomas.
You're welcome. That was a pleasure.